Okay, so this is where we stopped last time, and we came up with this formula. We said that now the difference between the this 1/3 Simpson rule or the trapezoidal, that if I have area that I want to find the integration between A and B, in the trapezoidal we assume that the relation between A and B is linear, and the minimum number of segments I can have is one, this one. So we assume that the whole area is from A to B, and we have the formula for that. Now, for the Simpson, it assumes that the relation between A and B is second order polynomial. So we'll have like a more of a curve or something, maybe like this or like that. Okay, and here we need to have another point, because to be able to find the interpolation function for second order polynomial, you need 3 points. So we take the midpoint, okay, which is A plus B over 2. Okay, so here we will have 2 segments. So the minimum number of segments that I can have for the 1/3 Simpson rule is 2 segments. If I want to have a higher order, then if I want to increase the number of segments, it increases in an even order, like 2, 4, 8, etc. Multiplication. It is a multiplication of 2's. Okay, so and we came up with this formula for the most basic one when n is equal to 2. It's equal to h over 3. H is the segment which is here, B minus A over 2, because as I said, you will have 2 equal segments here. F of A, so this is f of A, this is your f of A, plus 4 f of A plus B over 2, which is the function evaluated here, and finally plus f of B, which is the function evaluated there. So this is the rule if I want to use n equal to 2, now only for two segments. Now, as we did for the trapezoidal rule, we can expand this for an n number of segments. Okay, so here I can do the integration from A to B. Now h becomes B minus A over n. As I mentioned, in the minimum number of A segments is 2, so this could be B minus A over 2 as we have it here. Okay, but we could have 4, we could have 8, we could have as many segments as we want, and here n needs to be an even number. Okay, so we divide this into equal segments, and then we will find this, and your x of 0 is starting and x of n is your b. So here, as you can see, this is your curve. Okay, and now I have an n number of segments. So let's look from here between x0 and x2. There is here something that's not shown here, which is x1, and we know that x1 is nothing but the average between x2 x0, which is meaning it is equal to x2 plus x0 over 2. And here, for example, we will have x of n minus 1. So this is why we said always we will have three points in each one. So the integration from the starting to the end, or from A to B, or from x0 to xn, I will take the integration for each sub segment of that. Okay, so it's from x0 to x of 2, and we know that this is 2 segments by itself, plus from x2 to x4 until we reach from xn minus 1 to x of n. Now we will apply the 1/3 rule that we just showed in the previous slide for each segment. Okay, so the integration will be like, for example, here it will be x2 minus x of 0, x2 minus x of 0, which is your h here, f of x of 0 plus 4f of x of 1, which is in the middle, plus f of x of 2 over 6. This is exactly the same formula we have here. It's exactly the same formula. Now remember, h is b minus a over 2. So I can substitute this as b minus a over 3 times 2. B is the end, this is the beginning of the interval, divided by 6, which we have here. This is exactly what we have here, over 6. And we have here the beginning, the end, and in the middle. It's the same formula. So we will apply the same formula for each segment, okay? And then I will start collecting. So this is, this is plus, plus, extended until we reach to the end, from x of n to x of minus n minus 2. So we start from x2 to x0, which is the first one, until we reach to the last one. And we know that xi minus x of I minus 2, which is this segment for each one, it's 2h. Okay? And we know that I is an even number. Okay, let's move on now. So let's put everything in one slide. So your integration is equal to this. Okay, so this is for the first part, second part, n minus 1, and n part. Okay, now let me open the brackets. So we have here x0, x1, x2, x2, x3, x4. And so you will have even, odd, this is x0, we'll have odd, and you will have even numbers, okay? So we will collect the odd numbers together and the even number together, and we will have the the lower and the upper limits here. So I can write that in terms of a summation. And let's look to this. So this is the final formula for the number of segments, in number of segments. This is h over 3. We know h is nothing but b minus a over n. Okay. Now this is the beginning. So this is actually this is f of a, and this is at the end, which is basically f of b. Now in between, we will have here two summations. I goes from 1 to n minus 1, and I goes from 2 to n minus 2. We don't need to derive this, but if you collect the terms, you can see that clearly, that the odd numbers here multiplied by 4, the even number are multiplied by 2. Okay, so here this will be I from 1 to n minus 1, but I here is an odd number, so 1, 3, 5, 7, etc. And from 2 to n minus 2, but here I is an even number, meaning 2, 4, 6, 8, etc. So I can write this in terms of b minus a instead of h, and we know that h is b minus a divided by n. So we can have it in this format or in this format. So let's redo the same example that we did before using the trapezoidal rule, but now we will be using the Simpson's 1/3 rule to find the area. We'll have exactly the same function, it's a continuous function, and we will have the same limits from x equal to 0, which is a, to x equal 10, which is b. Okay, so we need to find the integration, and we will use 2 segments and 4 segments. So for the 2 segments, definitely what we'll have here, we will have in the middle, which is 10 plus 0 over 2, which is at 5. So we'll have here 1 segment, and here the other segment. Okay, so let's move on. So here these are the 2 segments. This is for n is equal to 2. Okay, now your h here is equal to b minus a over 2, which is n, b minus a over n, which is 2, which is equal to 5. So this is your h. This is the h. This is your h. So this is 2h actually, as I just mentioned before. This is 2h. Okay, excellent. So now the integration, I want to do it from a to b, second order polynomial. So f2 of x, d of x. So this is, I will write down the formula, h over 3 f of a plus 4 f of a plus b divided by 2 plus f of b. Simple as it, very straightforward. There's nothing there. So a, as we know it, we know that a is equal to 0, a plus b divided by 2 is equal to 5, and b is equal to 10. So these are the 3 points that we need to find our function. We know that our function f of x is equal to e to the power of x divided by 5. So I need to find f of 0. So we just substitute, which is equal to 1. I need to find f of 5. So it is e to the power of 5 divided by 5, or e to the power of 1, which is 2.72. And finally, we need to find f of 10, which is e to the power of 10 over 5, which is equal to 7.39. So we defined everything. We know everything now. So now we can find the integration. So I will just substitute here. So my integration that goes from 0 to 10 of f of x is equal to h5 divided by 3 f of 0 plus 4 f of 5 plus f of 10, and if we do that, we will this is equal to 32.12, which is very close. If you recall, the actual answer or the exact answer was 31.95. So from the beginning, we are getting very, very, very close with around 0.5% error. Okay. There's one question here. It says, could you please explain the 4f? Okay, 4f a plus b over 2. We derived that last class. However, what does it mean here? It is the function f. We know our function. Our function is f of x. Our function is f of x is equal to e to the x over 5. So this is our function. So this is f of x. Now this is a plus b over 2, or the middle point. I need to have this as 2 segments. So I will take the middle point between a and b. No, this formula was derived from the previous. At the end of last lecture, I derived that. Let me just go back here. Please, you go ahead. This is derived from here. When we start with the 3 points, a, b, and a plus b over 2, and we derive the formula from this. Okay, so you go there and you will find the whole. This is the derivation of this. Okay, so let's move on. Let's go back here. Okay, so this is 32.12, which is very close to the final answer. Now, if we go and try to find at n equal to 4 now, so now n equal to 4, meaning that your h, which is b minus a divided by n, which is 10 minus 0 divided by 4, which is 2.5. So now we have 2.5, 5, 7.5, and so we have here 4 segments. 1, 2, 3, 4 segments. And now my integration from a to b, and now I will use the more general formula. The one that we used in the previous slide is an exceptional case when n is equal to 2. But now I will be using the more general formula is equal to b minus a divided by 3n f of x of 0 plus 4, and we'll see how we'll use this now summation. As we said, I goes from 1 to n minus 1, and here n or I is odd number, plus 2, I goes from 2 to n minus 2, and this is f of x of I, and here I is even number, and here we have f of x of I plus f of x of n. Okay, so now let's try to do the calculation for this. Okay, so or substitute. So this becomes the integration from 0 to 10 of my function, which is e to the x over 5, d of x will equal to, okay, b minus a, so it's 10 minus a, which is 0, divided by 3n, n is equal to 4 segments. This is by definition in the question. Okay, starting of f of x of 0, f of x of 0 plus 4 summation of I goes from 1 to n minus 1. N is 4, so n up to 3. And here we have two terms. We will have I equal to 1 and I equal to 3, because I here in this summation is an odd number. So here we have my f of x of I plus 2. My I goes from 2 to 4 minus 2, which is 2. F of x of I. So for this, I will have only one term, which is f of x of I or x of 2, okay, which is 5 here, x of 2. So we have here x1, 2, 3, and 4, plus finally f of x of 4. So we have here defined what is x0, 1, 2, 3, and 4. Okay. So let's start the substitution here in this part now. So my integration will be equal to 10 minus 0 divided by 3 times 4 f at 0 plus 4 at or times f of 2.5, which is x1, plus f of 7.5, which is x3, the two odd numbers. If there is x5, then we add plus x5, but the maximum here is x4 only, plus 2 times f of 5, which is x2. Okay, and the last one, this is the limits here, so we don't have it here, we have it outside, plus f of 10, which is x4. So now we have all the terms. So when we do the calculations, we'll have this is equal to 32.088. See, there's no much big difference between this one and the previous one, which is when it is 32.12. They are very close, but this is also because the nature of the curve, as you can see, there is no abrupt changes, there is no sudden movement up high or low. So this is why this fits very, very well with the function. So here is the summary of the answer. So as you can see here, we are getting less than 1% after the first n equal to 2. Okay, if you recall, it took us a while before we reached this in the trapezoidal area. Okay, let's have this interesting question. It says here, I will start with n equal to 2. Okay, we have a function that we can easily find the integration. I want to do the integration from a 0 to 2, and then I want to find the error. What is the error? What is the difference between the exact and the summation, the approximation for n equal to 2? Okay. Now here for my integration, I is equal to b minus a over 6, 3 times 2, 3n, times f of 0 plus 4 f of 1 plus f of 2 not divided by 6. We already have 6 there, so there's no need for that. Okay, so this is your f of a, which is 0. This is your f of b, which is 2, and this is your f of a plus b over 2, which is 1. Okay, excellent. So we have now everything. Now we need to substitute f of 0, for example. This is your function. Okay, so your f of 0, we'll just substitute here. This is 0, 0, 0. This becomes 0.2. F of 1, again, you substitute here. This becomes equal to 0.225, 3 plus 8. So this will give you 36.2. Finally, F of 2 will give you 126.2. So we have all we need to find the integration for this. And this will be equal to 90.4. I will answer the question after I finish the question here. Okay, so this is the approximation with n equal to 2. Now this function is easy to find the integration. Okay, so let's find the integration for this one. Integration from 0 to 2, 0.2 plus 25x plus 3x squared plus 8x cubed d of x. So this is equal to 0.2x plus 25x squared divided by 2 plus 3x cubed divided by 3 plus 8x to the power 4 divided by 4 from 0 to 2. And surprise, surprise, when we find the answer, it is 90.4. So we have exactly the same answer as the approximation, meaning that this function has an error equal to 0. And if we recall, we said that in the trapezoidal, if the function f of x is the first order, a0 plus ax, the error will be what? The error will be 0, only if we have first order. Okay, and the reason, because we found that the error is proportional to the second derivative of x. So when you take the second derivative of this, you get 0. Okay, so if the function is linear, first order polynomial, then you get a 0 error. Now here we have a function of third degree, and yet the error is 0. Okay, so we need to understand, if I use the Simpson method, what is the relation between the error and the order of the function, and this is what we want to derive. But before that, let's see the question here. We could use the other variant of the formula, since here n equal to 2, right? I didn't get your answer. We could use the other variant of the formula. What do you mean by variant of the formula? Since here n equal to 2, I mean the other form of the. You mean the other form of the formula? Yes, yeah, yes. Here we use the other form. I mean, this form is exactly the same as the other one, but this, I mean, we can apply. Let me show it to you. Let me show it to you. This is the general formula. Let's go back. Let's go back here. Okay. Now, this is the general formula. Okay. Now, for n equal to 2, let me substitute here. N equal to 2. So this becomes 2 minus 1, and this is 2 minus 2. Okay. And this is A, and this is B. Okay. Now, this is I goes from 2 to 0, so there is no item here. This is I goes from 1 to 1. You will have only one item, which is x1. But what is x1? It is a0 plus xn over 2, or a plus b over 2. So this becomes a plus b over 2. Okay, and this n becomes 2, so b minus a over 6. So this is the general formula. So if n is equal to 2, the previous formula we have, it's just a special case of it. Okay, so it's exactly the same formula. There's no, you can use this formula and you can apply it for anything. Now we want to understand the question is why we get exact solution here. So let's neglect, of course, the round off error, and we want to concentrate on the truncation error. Oh, these two terminologies looks very old. I mean truncation error and round off error. round of error, as we mentioned before, when you round the number, truncation error, when you round the process. Okay, so truncation error because here we have a limited number of n. Okay, so if you increase the number of n, you are reducing the truncation error. The more n you have, the less truncation error you have. So this is to deal with the process. The round off is to deal with the number itself. Okay, so let's see here now. The integration that I'm interested in is goes from x of I minus 1 to x of I plus 1. Remember, here I is an even number. This is 2. Okay, so here if this is your function, so if this is x0, this has to be x2 because you have to have a third number here, x1. Okay, so this has to go from 0 to 2. So this is why we have xi minus 1, xi plus 1, and there's an xi as well in between. Okay, so this is why it is from not from xi to xi plus 1 or xi minus 1 to xi. There is a third number which is xi, which is between these two limits. F of x, e of x. So we'll do the same approach, the same procedure that we did in the previous set of notes, when we derived the relation between the error and the order of the derivative of the function. So this is basically f of x of I plus 1 minus f of x of I minus 1. And we know now from our previous discussion that I will use Taylor expansion for both items. I will find the Taylor expansion for f of x of I plus 1 and f of x of I minus 1, both of them. So let's start with f of x of I plus 1. Okay, so this is now, as we know, xi plus 1, this is plus h, because we have two h's in the both side. We know that this is here, this is, as we mentioned, this is an h here, another h here. So x of I, which is here in the middle one, x of I plus 1, to go to the right, you have to add an h to it. So this is exactly is equal to f of x of I plus h. Now, we can expand this, is equal to f of x of I plus h, f prime of x of I plus h squared over 2 factorial f double prime of x of I plus h cubed divided by 3 factorial f triple derivative of x of I plus h4 divided by 4 factorial f to the power of 4 of x of I plus h to the power of 5 factorial f to the power of 5 x of I, and so on and so forth. Now, if I'd like to find f of x of I minus 1, it will be exactly this formula, but whenever we have, this will be equal to f of x of I minus h. So I will substitute every h with minus h. So this will become minus, this stays positive, this is minus, this stays positive, and this is minus or negative sign. Okay? So now I have a formula for f of x of I plus 1 and f of x of I minus 1. Okay, very good. Now let's move on here. And then I will subtract both of them. I will subtract this from this, okay? And we know from our previous discussion that f prime of x equal to f of x. We mentioned that before. Okay, so now if we do this, take the integration, which is basically the f of x of I plus 1 minus f of x of I minus 1, and substitute, we will get this formula. And this is for our exact answer. Now, we know from our previous discussion that the second derivative of x of I, we derived this formula before, is the f of x of I plus 1 minus 2f of x of I plus 2f x of I minus 1 over h square, and this is the error for the second derivative. We mentioned that in the derivative part. So if we substitute here, you will find that this is the formula for the integration and the error. And guess what? The error is a function of the fourth derivative. This is why in the previous example, when we have a polynomial, a third order, if I take the fourth derivative of this, you will get 0. Of course, here we'll be having a higher order derivative, which doesn't matter, because if it's 0 at the fourth derivative, at the fifth, at the sixth, it will be also all zeros. Okay, so this is the formula that we have now. We'll do exact. So this is from our previous. This is our integration for the segment, and here is your integration. Okay, so and this is from previous. So this is my integration, as I mentioned. So here, this is what we derived. So this is your formula. So your AI is equal to h to the power of 5 over 90, the fourth derivative. So we will do exactly what we did last time, which is we will estimate the fourth derivative is less than or equal certain number m. So e of I is equal to this. And finally, this is the formula for the error, which is equal to b minus a over 180 h4 times m, where m is the maximum value of the fourth derivative defined in the whole interval from a to b. Okay, and this formula is exactly the same as this formula, because we know that h over 2 is an n. H over 2 is n, then n will cancel with each other. Okay, so let's repeat the same example we had in the trapezoidal when we say that I want to see how many ends, how many segments do I need to limit my error to 10 minus 4. This is exactly the same example we have. So we know that the error E of t is less than or equal b minus a h to the power of 4 divided by 180 m. So I have two unknowns here in this, b minus a. I know it, of course. This is 2, and this is 0. Now h I want to find. M is the maximum, so we value of the fourth derivative. If you take the fourth derivative, you can try this yourself. This is 24 divided by x plus 4 to the power of 5. And obviously here, if we try to find this from 0 to 2, the higher the value, the lower this number. Very obvious. So the maximum you can get it is at 0. If 4 at 0, and this is equal to 3 over 128. So I know m now. So the only thing that I need to find is h, actually. And we know that this is 10 to the minus 4. So from this h, which is equal to 2 over n, will be less than or equal to the power 2 divided by 5, fourth root of 15. And from this, you can find n is more equal to or more than 4 segments only. So we achieved the same degree of error. Remember there, when we have a trapezoidal, n was greater than or equal to 15. I need 15 segments. Here I will need only 4 segments because of the nonlinearity that we assumed in the function. We could reduce the error and have a much faster convergence.